way. Some people find this simpler. What we do here is we use these equations which we wrote down earlier. The equations are dv dx equals q. In case when there's a load acting downwards, that equation is q is minus w. And so we can then take this equation and write it as dv equals minus w dx. And so when you integrate this from, let's say, section 1 to 2, you get v2 minus v1 equals minus w dx. Now, so what we can see that if there is a concentrated load, example would be P equals, let's say, 150 kilonewtons, like the ones we've seen before. If there's a concentrated load, then Q is 0, right? Because Q stands for distributed load. In this case, dV by dx equals 0. If the change in shear force as a function of x is 0, it means that V is a constant. Okay. So that's 1 second. If there is a distributed load, e.g., say 40 kilonewton per meter, in this case, we can integrate that equation. We'll see that V2 minus V1 equals minus 1 to 2 minus W dx. So W is a constant, so it comes out of the integral. And so we have minus W x. The integral of dx is x. The upper limit for that is whatever it is at 2, so x2 minus x1. So you see that V of x is a linear function of x, which means that it will be a straight line.
This might be a dumb question, but like, so this concentrated load like Q equals 0,
because this stands for distributed load. You can see that Q is dV dx. The units of Q, something like kilonewton per meter, something like that. It's not kilonewton. In fact, if there is so that's the definition of shear force. The units of this is kilonewtons. Yeah, we can. Okay, so the reason I'm writing this is I'll try to attempt the same problem using these equations, and I think that they're more intuitive. You don't have to really start writing all those equations for shear force, shear force and bending moment equilibrium, which we have written down. Just much easier to do it. So I'll just show you this way of doing it. So it'll make, for some of you who like it, make it easy for you to solve the problem. So we can have a similar analysis for the bending moment. The equation we wrote down for bending moment is Tm dx equals change of rate of change of m with respect to x is shear force. And now we can do the following, which is, well, first let's integrate this. Dm equals v dx. Let's say we integrate this from 1 to 2. So on the left side, since m, we just have dm, it would be moment at 0.2 minus moment at 0.1 equals 1 to 2 v dx. So now we have two cases, and we won't go beyond these two levels of complexity. One is v is constant. Okay, so you look at the shear force diagram, you'll see that the shear force is constant. It could be 0, it could be 5, 10, whatever, but it should be a constant. If it's constant, then we can pull out v from this equation, and we'll have m2 minus m1 equals v dx 1 to 2, which is v x2 minus x1. In other words, m as a function of x is a linear function of x, which means that if you look at the bending moment diagram, m will be a straight line. The second case is v is, so v of x is v times x. Okay, well, this happens when you have a distributed load, like we've seen in, you just go back to this question. So when we have a line, a straight line, we'll see a quadratic curve, right? That's what this second example hints at. So if v is a function of x, linear function of x, then integrating this would give me m2 minus m1 equals integral. So now I cannot quite, well, let me just sub in this value here. So let's start it as v of x dx, which is v, I can pull it out, it's constant, x dx. So the integral of x dx x square divided by 2, and then at the upper and lower limits gives me vx2 square minus x1 square divided by 2. So in other words, what it's saying is that m of x is a quadratic function of x. Can we see it here, which is, so when we had constant for v, it became a line on the moment equation. When it was a line with a linear function of x like this, it became quadratic. Okay, if you go down one more problem where we did that, you'll see the same thing is true. So what I'll do next time is I'll use this equation, this logic to resolve that problem, and hopefully that is much simpler than what we've done so far. So that's the problem we were solving, and I managed to finish this problem. It took the whole class to solve this. We use this equation, dv dx equals minus w. Okay, so I'm just going to draw the shear force diagram without actually writing any equations. Well, we might have tried one equation for the straight line, but other than that, we can pretty much draw it without having to do much math. This v is a function of x. Okay, so dv dx equals minus w. If w is 0, then dv dx is constant. If, however, there's a point load like there is 133.75 upwards, then all I need to do is put that much of shear force on the figure, which means that I should just put 133.75 on over here. So it starts up at 0, but there's a load acting upwards. So I just go up 133.75. Okay, after that, we see that from A, moving on to the right, we have the distributed load. So this is where we need to possibly integrate this equation. So let's integrate that equation. So dv equals minus w dx. We need to integrate from A all the way to, let's just integrate to some distance x, okay? And then that distance x can also be made to be 8 meters, in which case we will have point B. dv equals minus, so we know that w is 40, x, that's the force, sorry, my bad, 40, just 40, dx, integral from A to B, so A is 0, B is x, just change this to 0. So this will give us V at x minus 0 equals minus 40x. X is upper limit, lower limit is 0, which is minus 40x. No, I'm doing something wrong. This is not 0, right? Because you see that the shear force is 133.75. So I need to put 133.75 there. Okay, which means that the equation is Vx equals 133.75 minus 40x. Okay, so now it makes sense because if you put x equals 0, you see that the shear force is 133.75. And then we can put some other value for x and find the shear force at a different point. Remember that x only varies from 0 to 8 because that's the region which we are looking at. The load is distributed. So this equation is true for 0 to 8. Do not use it beyond 8. Okay, so let's just put x equals 8. Right? You could use any points. So you get Vx equals 133.75 minus 40 times 8. So it's 133.75 minus 320. And that comes out to be 186.25. So we have, in effect, one more point at x equals 8. I need to go right below here, right below B. And then that's about, say here, 186.25. And so I need to join those 2 points. So clearly, if you join those 2 points, there's a point at which the shear force is 0. If you want to find the location of the point at which the shear force is 0, so we want to find x when v equals 0. All we got to do is, in this equation, we got to put Vx equals 0 equals 133.75 minus 40x, right? We're solving for x now that we know that shear force is 0 at some point between A and B, and solve for x. So I get 3.34. Okay, so this is of some interest when you are talking about stresses and in the later part of the course. So I'll just show you how to do that just in case you need it later on. Okay, so we integrate that equation because there was a distributed load. Now we can again go back to not really doing much with the equation. We just have to see how things change as we move. There are only concentrated loads beyond B. So at B, we see that there is a load which is going upwards, right? So all I need to do is take 186, so minus 186.25, add to it 206.25, because at B, that's the load which is acting upwards. This comes out to be 20. So go up. till 20. And then as you go from B to C, you see there is no point load, nor there is any distributed load. And when that happens, the shear force V has to be constant, right? Because if you put W equals 0, dV dx is 0, V is constant. So we would have a constant shear force of 20, whatever it was at B. But then at C, the shear force goes down because there's a force from upward to the downward direction, and that's going to make it go back to 0. This is going to be 20, which we have there, minus 20 from force at C. And so we end up at 0. So we start at 0, end at 0, as you would expect it. Okay, so hopefully that was easier than what we did last time, where we took different parts of the beam, cut it, and wrote the equations of equilibrium. Yeah, yeah.
So when you take the interval dv 0 to x, how did you just come up with that? When you integrate from 0 to x, where do you just d of x?
This integral.
Yeah, how did you get negative 130?
Yeah, so this is the shear force from 0 to x. And I just need to look at the shear force diagram. Here it's 133.75, and that comes because of this force. It's not 0. Yes, so this is like the way this works is there is a force, and if you zoom in here, right, 0, it's 0 right here, but then the moment you go slightly to the right, the shear force is equal to 133.75. And then when you're integrating it, you're passing through the point 0. And so you have to take into account 133.75. It's not 0. It's a discontinuity, as you can see, right? It suddenly jumps from 0 to 133.75. But when you're integrating it, you need to look at 133.75, because when you go from 0, you have to pass through 133.75 to integrate out px. There is a force. Yes, so if it's an overhanging beam, something like this, let's make it the other way. And let's say there is a force like this, and then we are integrating from here. Yeah, so Vx over here is 0. In fact, the shear force diagram for this will be, assuming that you've drawn the free bar diagram and you've got R. In this case, I think it will be like this. This will also be P. So then it will be, the shear force diagram will be 0. It will jump up, go there, come down. So the shear force here is 0. Yeah. Okay, so now that we've figured out the shear force diagram, let's look at the bending moment diagram, for which we'll use this equation. dm dx equals v. Okay. And the thing about this equation is that when you integrate this, you have m, let's say from a to some point x, a to some point x, mx minus ma is area from a to x on vx curve. Okay, so the beauty of this is that that particular equation I wrote down, which is mx minus ma, can actually be used to solve for the moment diagram without actually writing any equations. Just by reasoning about the area under this curve, vx curve, we can actually draw the shear bending moment diagram. I'll show it to you in just a bit. Let's draw the axis. So this is the point A, and this is about where B is. And this is where C is. Okay, so now what we'll do is we pretty much go to the Vx curve and find the area under the curve for different geometries. So let's start off with this. So that area is, so area of a triangle is half base times the height. So the base here is 3.34. The height is 133.75. And that comes out to be 223.36. That's this area. Similarly, we can find this area. It's going to be half. Okay, so with a negative sign, of course, because this is below the x-axis. So negative half times the base. So the base here, this is 8. So it's going to be 8 minus 3.34 times the height. The height is 186.25. So that comes out to be minus 433.96. And then finally, this area is just the area of a rectangle, base times height. The base is, remember this point was 11. So 11 minus 8 is 3 times the height, which is 20. So that's 60. Okay, so that's all we need to draw the shear force, sorry, the bending moment diagram. So you start on the left side where the shear force is 0. And so again, it's going to be area under the curve for the left, the area for the curve under the curve right over here, which is from 0 to 0 is clearly 0. So that should be the first point. Then we have the shear force is, well, it's 223.36. The area under the curve from 0 all the way to 334 is positive, which means that up to 3.34, we should have this point, which is 223.36. So anything which is an area on the Vx plot will be a y coordinate on the right side, right? Because of this relation. Area which is on the right side equals some coordinate on the left side. So that's just one point. I'm not still done joining A and B, sorry, A and this point, because I do not quite know if it's a straight line or something different, which we can actually reason again from looking at that equation. Then we have minus 433.96. And what you need to do for 443.96 is you need to subtract that out from, that is, you need to add that to 223.36. So 223, right down here, 223.36 minus 433.96. And then that comes out to be 210.6. It should be negative, and I think I'm missing this. This should be this is 36, 36, and this should be negative. So that point is right here, minus 210. Okay, so I need to connect this point A with this point, and then this point at B, right? And what helps me here is to look at how V is a function of X. So V as a function of X is a straight line. So if it's a straight line, then the integral, so V is constant, sorry, is a straight line. V is a function of X, right? From A to B. If V is a function of X, then when you integrate M for M, area V dx will be V of X, which will be a quadratic. So from A to B, there is some underlying quadratic equation. So if you want to, well, when you're answering this in the exam, all you need to show is that there's a curve. But if you want to find the exact curve, then you need to do more than just connect them by a curve. You need to basically find the area from here to here, right? Just like you did this area, you can find areas of different triangles, and then keep putting those ordinates, and then you'll get exactly this point, and that's how you connect it. But I only want you to realize that it's a quadratic, and as long as you show it to be some kind of a curve, you're good. Something like that. So this is showing that the moment reaches its maximum at x equals 3.34. Okay, the final step is to go from B to C. So from B to C, we have area under the curve is 60. So all I need to do is minus 210 plus 60, which is minus 150. So at C, we'd have to go up to 150. And now the question is, how would you join the points from B to C? You look at the VFX curve, it's a straight line, but it's a constant. If it's a constant on the VX curve, then it should be a straight line on the MX curve. Because again, if you can look here, V is constant, then integral of V dx becomes out, it becomes integral of dx. Integral of dx is x, and so it's a straight line. So I just need to draw a straight line. Okay, and then finally, there's a 150 kilonewton meter moment on the right side. That actually ensures that the moment here is close to 0. That is my MX curve. And as you can see, I practically wrote no equations except for this equation, which is what I used in order to get that curve. Yeah. The first one? Sure. So from A to B, if you look at VX curve, V is approximately V of X is something like this, V times X. Now, there might be a constant and so on, but it's basically a constant times X. It could be C, MX plus C, whatever you like. Well, all I care is that it's a linear function of X. So once I have that, then MX minus MA will be integral V dx. I'm just rewriting this equation. But V dx is integral Cx dx. So C comes out. And so we have integral x dx, which is something like Cx squared divided by 2. And so we see that it's it's a quadratic equation.
We are looking at the equation which we made from the VX diagram.
Yes. Yeah. So right. So the thing about this particular method is that you need to have the Vx curve in order to draw the Mx curve. However, if you look at the previous method, let's go back here. This one on the right side, you actually do not require to know what V of x is, because you never really use V of x on the right side. You can see the V of x actually cancels off because you take moments about that point. So if you're asked to find M of x only, you can just use this method and you don't have to do any of the, you don't have to draw the Vx curve. But if you want to, if you're asked to draw the Vx and the Mx, then I think you're better off trying to use this method, which is easy, I think, personally, because you just look at the equation, dv dx equals minus w to get that curve. And then on the right side, you look at the curve on the left side, the VFX curve, in order to find the M of x.